All right, today we're going on a bit of a detective mission, deep into the world of C and C++ programming. We're hunting for a really sneaky culprit called memory corruption. You know, the kind of bug that causes those mysterious crashes and, worse, serious security holes. So let's gear up and dive in to learn how to track these things down.
Here's our game plan. First, we'll get a handle on the problem itself, kind of like sizing up the crime scene. Then, we'll look at the two big investigative paths, white box and black box. From there, we'll get into the nitty-gritty of inspecting source code and testing live programs. After that, I'll show you a secret weapon your compiler has been hiding. And finally, we'll see how finding the bug is the biggest step toward fixing it. You know, every good investigation has to start at the beginning. Before we can even think about catching our bug, we need to know exactly what we're looking for. So let's head to the scene of the crime.
So what is this culprit really? Well, according to MITRE, memory corruption is what happens when your program writes data to a place in memory it just shouldn't. Think of it like a mail carrier putting your mail in your neighbor's mailbox by mistake. It might seem harmless at first, but it can cause total chaos later on, leading to crashes, totally unpredictable behavior, and yeah, some major security holes. And that right there is the central mystery we're trying to solve. These bugs are incredibly good at hiding. They might not cause a problem right away, which makes them insanely difficult to track down. So the real question is, how do we find them?
Well, in the world of bug hunting, there are basically two fundamental philosophies, two main paths our investigation can take. Let's break them down.
On one side, you've got white box testing, which we also call static analysis. This is when we have the program's full source code. We have the blueprints. On the other side, there's black box testing, or dynamic analysis. That's when we're testing the program while it's actually running, without seeing a single line of code. It's kind of like the difference between reading the script of a play versus watching the final performance.
Okay, let's dive into that first approach, white box testing. This is where we get to put on our detective hat and go through the original blueprints, line by line, checking every single detail before the program is even run. This is what we call static analysis. So with the source code right in front of us, we have two main ways to go. We can do a manual code review, literally reading it line by line. Now, that gives you a super deep understanding, but wow, is it slow, and it's really easy for human error to sneak in. The other option is to use automated tools that scan the code for common mistakes. They are lightning fast, but, they can sometimes raise false alarms. And this brings us to a really crucial point. While those automated tools are awesome, they are not perfect. They aren't foolproof. They can definitely miss more complex or unusual bugs, which is exactly why a good detective never relies on just one tool. You gotta use everything in your arsenal. So what if you don't have the blueprints? What if you can't see the code? Well, that's where our second method, black box testing, comes into play. With this dynamic analysis approach, we're basically putting the suspect under observation, testing the program while it's live to see how it behaves under pressure. A really key technique here is something called fuzz testing. This is where we just bombard the program with tons of invalid, unexpected, or just completely random data, all to see if we can make it crash. It's kind of like shaking a vending machine to see what falls out. In fact, this is how huge vulnerabilities, like the famous Heartbleed bug, were found, just by throwing weird stuff at a system until it finally breaks. And speaking of tools that can help with this, one of the most legendary tools in any developer's kit for dynamic analysis is Valgrind, and specifically its memcheck tool. It's been the go-to for years for a very good reason. And using it is actually pretty straightforward. First, you install it, then, and this is important, you compile your program with the -G flag, which tells it to include a bunch of useful debug info. Then you just run your program through the Valgrind command. It sits in the background, watches everything your program does, and spits out a detailed report if it catches any memory errors. So we've covered the classic methods, the tried and true stuff. But what about the high-tech gadgets? Well, it turns out the very tool you use every day to build your program, your compiler, has some incredibly powerful secret weapons built right in. Honestly, your first and easiest line of defense is just to turn on more compiler warnings. Flags like wall and wextra basically tell your compiler to be super strict. It's like having a partner who double-checks all your work, catching potential problems before they ever become real bugs. It's free, it's easy, and it's a powerful bit of static analysis you get for almost no effort. But as helpful as those warnings are, they can't catch everything. They can only see what's right there in the code. They're only half the story. For the really sneaky bugs, the ones that only pop up when the program is actually running, your compiler has an even more powerful trick up its sleeve.
I want you to meet Address Sanitizer, or ASN. This thing, developed by Google, is an absolute game changer. It works by creating what it calls shadow memory. Think of it like a security guard who has a master list of every single valid memory address your program is allowed to touch. And as your program runs, if it ever tries to access an address that isn't on that list, bam, ASN catches it red-handed.
And here is the best part. It is ridiculously easy to use. You just add one single flag when you compile your code. That's it. Then you just run your program like you always do. If a memory bug happens, ASN stops everything and gives you this beautiful, detailed report showing you exactly what went wrong and on which line of code. It's just amazing. So, we've gone over the crime scene, and we've explored our entire toolkit, from manual code reviews and fuzzing all the way to amazing compiler tools like Address Sanitizer. We now know how to find the bugs. And that brings us to the final, most satisfying step, closing the case. And here's the most important thing to take away from all this. Tools like Valgrind and ASN don't just tell you that something is wrong, they give you a stack trace. They point you to the exact line of code that caused the problem. They lead you directly to the culprit. Finding the bug is more than half the battle, and these tools make that part easier than it has ever been. So there you have it. You are now equipped with a full detective's kit for hunting down some of the absolute trickiest bugs in programming. That path from a mysterious crash to a solid fix should be a whole lot clearer now. So the only question left is, with this power to write safer, more robust software in your hands, what are you going to build next?